Hiya, this is James and we're just going to do a few videos on number systems for this playlist. And the first one that we're going to have a look at is what the common number systems are. And the ones that I often use, and they're often used in engineering and computing and things like that, are base 10, base 2, base 8 and base 16. So like I said before, they've all got the same sort of format. They've just got a different number as their base, and that'll become clear what that means when we do a few examples. So obviously I'll do these color coded. So for base 10, if we've got a number like 37, what we should really do is put the base as a little subscript number so we can tell the reader exactly what the base is. So now we know it's 7 units and 3 tens rather than 7 units and 3 something else like 3 16s like it would be in hexadecimal. So we always put the base as a little subscript number to the bottom right. Okay, so with any number system, the first column is the units, because that is the base to the power 0. Anything to the power 0 is 1. If you wanted to know why anything to the power 0 is 1, say you've got x cubed divided by x cubed, or anything over itself is equal to 1, but also when you divide of the same variable, what we do is subtract the power. So that is actually equal to x to the power 3 minus 3, which is x to the naught. So anything to the power naught equals 1. And that's where that comes from. So you can look that up for yourself, but pretty much that's a quick way of proving it. So base 10, we've got the units, then we've got the tens, which is obviously, well, the units is the base to the power naught. The tens is 10 to the power 1. We've got the hundreds, which is the base squared. Then the next column will be the base cubed, which is 10 times 10 times 10. And then the base to the power 4, and so on in each direction. I'm just going to use the same columns, but do the different bases one on top of each other, otherwise we'd have to keep doing new pages all the time. So for binary is base 2, so we would write a 2 next to the numbers that we're writing down to show people that it's binary and not say decimal. With binary, because it's base 2, there are only 2 unique characters in this number set. There's no other ones apart from 0 and 1, because that's the first one, that's the second one, and that's all we've got to represent numbers with. So with binary, the first column is the base to the power 0. Anything to the 0 power is 1. Then the next column is worth the base to the power 1, which is 2. The next column is the base. Binary has the base of 2, so it's the base squared, which is the 4. The next column is the base to the power 3, which is 2 times 2 times 2 is 8. The next column is the base to the power 4, which is 2 times 2 times 2 times 2, which is 16, and so on. And the fractional parts, after the radix point, it would be 2 to the power minus 1, so the halves would go over here, and then the quarters and so on. So you can see there's a lot of similarity. The only thing that's different is the base. For octal obviously is base 8. That's quite a common number system. I never used it as a kid. Don't really see the point of it really, but it's in a lot of books. And also it's used in things like Unix file permissions where there's 8 different variables, but I don't see why they can't use binary or hex really, but there you go. Octal, the first column is always the units, which is 8 to the power 0 is 1. Then you've got 8 to the power 1. The next column is your 8s, and then your 8 squareds. 8 8s are 64, and then your 8 times 8 times 8. 8 64s are 512, because it's 8 6s are 480 and 8 4s are 32, and so on. And then 8 of these will be 4096, and you'll get used to these numbers the more you use the number systems. It's like familiarity, you know, it becomes second nature then. Another common number system that is used in engineering and computing is hexadecimal. The reason that we use hex is because it's like a shortened way to more easily read binary, and that's really the only point in having hex, if you ask me, is because a long string of binary ones and noughts, you can make it 4 times shorter by using hexadecimal, and that's about it really. Hexadecimal, hex is 6, decimal's 10, it's like hexadecimal or base 16. So the first column of hex is the ones, which is 16 to the power 0, then 16 to the power 1 is worth 16. Your next column is your 16 squared, which is worth 256, and the next column is 16 times 16 times 16, or 16 cubed, which is 4096, and then the next column is 16 to the power 4, which is worth 65,536, and each time you go left the column's worth 16 times more, and each time you go right you divide by 16, it's worth 16 times less. And what I didn't say earlier, for base 8 there are 8 unique characters, which are 0 and 1 to 7. For hexadecimal there are 16 unique characters, which are 0, I'll write all these down, 1, 2, 3, 4, 5, 6, 7, 8, 9. But then we also have A, which is worth 10, B is worth 11, C is worth 12, D is worth 13, E is worth 14, and F is worth 15. So we can squeeze more numbers into a single column by having different characters. We could have gone on to, like, you know, more and more letters, but 16 is a convenient base because it's it fits in well with octal and binary. So they're the unique characters, and we all knew the unique characters that we're allowed in decimal or base 10 is 0 and 1 to 9. So we cannot put 10 in a single column. It becomes 1 in the next column and 0. So there are 10 unique characters with base 10. So this video, I'll leave it there because we've figured out what the columns are worth for various number systems, but next we're going to start on the next few videos converting between the different number bases. Alright, thanks.